In this example, we're being asked to integrate a pretty nasty looking expression. And so first thing we have to do is decide what technique might be helpful here. So what should go through a student's mind when they see a problem like this? Well, first thing I would try all the basic techniques. Might be a U substitution. That would be worth a look. I don't think that it is, and you can try out that some of that that algebra there. You can let the u be 1 plus x squared, but you can easily see this isn't du. It might be an inverse trig integral, but again, I don't think it is. Again, this 4x cubed is giving us some trouble. But what should catch our attention after we try all of those is the fact that this is of the form the square root of a squared plus u squared. That's what should catch our attention, and that's what I noticed, right? So if it is of this form, then it might be one of these trig substitution problems that we've been studying lately. And so here's what we're going to do anytime we have a trig substitution integral, or what we think is a trig substitution integral. We are going to start by drawing a right triangle, and I think this is a very important part of doing these guys. So make sure that you literally draw a right triangle in your paper. And as we know, the idea behind trig substitution was to write this radical expression on one of the legs or the hypotenuse, right? And then we can find a trig relationship that would mean the same thing as the radical. So the big question is, where do we put this guy? Now, the way I teach this is not to rely on a chart where, a textbook says, if you have this, then you do this, or if you have this, then you do this. Let's just think about it. I think we can just logically think about where this guy should go. Because he has a plus, I feel that he would be best put on the hypotenuse, square root 1 plus x squared, so that this edge can be a 1 and this edge can be an x. And so you would have, I'm going to erase this, but you would have 1 squared plus x squared equal to the hypotenuse squared. That's the Pythagorean theorem. A squared plus b squared equals c squared. And notice when the square root and the square cancel each other, these match, right? These match. And so again, I put him on the hypotenuse because that was a plus. If it was a minus, I would have put it on one of the legs. That would have worked out best. All right, but choosing this as our right triangle, then we have relationships that use the radical and that use x. Let's write them down. The one that would incorporate theta with x, namely theta, x, and the constant would be easiest, would be the tangent relationship, and you would get x equals 1 times the tangent of theta. And the one that would incorporate the radical, preferably with the constant, would either be cosine or secant. And I think I'll prefer secant. We'd have the square root of 1 plus x squared equal to secant of theta, right? That's hypotenuse over adjacent as opposed to adjacent over hypotenuse. So I can take these guys and stick them in the integral. And so I will have something for the radical, something for the x, and I can cube it just to get an x cubed if I need to. But notice I'll also need the dx. So while I'm at it, let me just go ahead and find him as well. If this is x, what would dx be? That would be the derivative for tangent, which would be secant squared theta d theta. So now that I have these guys written down, it's time to rewrite this integral. Let me change colors here. We'll do it right here. This would become the integral of what? Well, the denominator with the radical would be secant of theta now. That's the same thing as the square root expression. The numerator would be 4x cubed. So we'd have 4 tan cubed of theta. And then the dx would be secant squared theta d theta. So this is a new integral that's equivalent to the old one, but it has trig terms instead of radical terms. I would prefer this guy. I would prefer the one with the trig expressions in it. Now I do see some good algebra. I see that this secant will cancel with one of these secants. And so we'll get integral of 4 tan cubed theta times secant theta d theta. Let me write that on the next page. We have the integral of 4 tan cubed theta times secant theta d theta. This is a trig integral, which hopefully we can do. Now, this is a whole other topic. This is a whole separate scenario. But remember, when you have secants and tangents, there was a way you were supposed to integrate these guys. It did not really have anything to do with the whole radical discussion. This should be known from another set of videos about trig integrals. But basically, when you have secants and tangents, the idea is to save some of these terms at the end to be like your du, and write the rest of the terms in terms of u. And so some trig derivative would be the du, where the original trig expression would be the u. So I think here it would be very nice to save a secant and a tangent. So we have secant theta and tan theta. And that would be a great du, because secant tangent is the derivative of who? Secant tangent is the derivative for secant. Secant's derivative is secant tangent. Now you might say, well, Devin, I don't know if that's a good idea, because what you have remaining is not secants, it's 4 tan squared theta. So now let's think about this for a minute. How can we handle this? What can we do? What can we do if we have a tan squared theta and I would prefer to have secants instead? Well, hopefully you know exactly what we need to do. There's a trig identity that relates tan squared with secant squared. I'll jot it up here in the corner. Secant squared theta is equal to 1 plus tan squared theta. That's a common trig identity that we should already know. So if you want tan theta, then that would be equivalent to secant squared theta minus 1. So we'd have 4, and I don't really need this 4. Let me just pull the 4 on the outside. You would have secant squared theta minus 1 quantity times secant theta tan theta d theta. All right, so we're trucking right along. This part at the end could be a du if the u was equal to secant theta. So we have basically u squared minus 1 du. That's perfect. U squared minus 1 du. Matter of fact, let me write that down. So now we have 4 times the integral of u squared minus 1 du. And I can integrate this guy. This will be 4u cubed over 3. U cubed over 3 times 4 minus 4u. Where really I just integrated u cubed over 3 minus u, or that was the integral, and then we put the 4 back in there. All right, plus c. All right, so now we have a fair amount of work to do. This is kind of our answer, but we still have some work remaining. Remember, this was u substitution, so u was actually equal to something. This was 4 u cubed, but what was u? U was chosen to be secant. U was secant theta. So this would be 4 secant cubed theta over 3 minus 4 secant theta plus c. All right, but unfortunately that's not our final answer. You have to hang with me for a moment longer. The original integral wasn't in terms of u or theta. What was the original integral given in terms of? It was given in terms of x. And so now the question is, can we write secant of theta and all these sorts of things in terms of x? Well, here's where the right triangle becomes so helpful. You can write any relationship for theta with respect to one of these sides or two of these sides, because we know sine and cosine and tangent and secant and cotangent are all ratios of these sides here. So for instance, if we needed secant, what is secant? Secant of theta is hypotenuse over adjacent, which would be the radical expression. So where was it that I had a secant? I had one right here. So we'd have 4/3 and then we would have something cubed. But what was it that was cubed? It was the square root of 1 plus x squared, and then minus 4, and then there's that secant term again. This will be the square root of 1 plus x squared plus c. All right, so this is our final answer. I think it would be fine to leave it this way. If it kind of bothers you having the radical and the power, we can fix that. Matter of fact, I think I might just finish out this problem, fixing this one little thing right here. We would have equals 4/3. Let's look at this. If you have something that has a square root and a cube, then that would be to the 3/2 power. Square root is 1/2, cubed is third power. So we'd have 1 plus x squared to the 3/2 power, and then minus 4 square root of 1 plus x squared plus c. All right, so great example here. We started with a really tough integral that we had no techniques for, no techniques at all. But we did an appropriate u substitution without memorizing anything. We did all this on the fly. We used our right triangle to find some nice relationships. We substituted the trig expressions in instead of the terms with the radicals in them. That helped us do the integration, right? We could do the integration with the trig functions in there. And then after this step, from here to here, this started off kind of looking like our answer. The only problem was this had u's, and then once we substituted the u's back in for what they were equal to, secant of theta, then they had thetas, and then we had to do one more step to get our x's. So yes, some of these take a while, but I still find it very impressive that we have some way of doing these integrals. So I am thankful that we have u substitution, or trig substitution rather.